Our next talk, our next speaker is going to be Morteza Kerachian. Hello.
Hello, good afternoon.
Okay, good afternoon. So please, can you start your sharing?
Okay. Is it okay?
Yeah, maybe full screen, a little better. Perfect. Thank you very much. So go ahead. Thank you.
Today I want to talk about the dynamical analysis approaches in spatially curved FRW spacetime. And my talk is based on two papers that I did with Giovanni Opava and Gorgios Kerachian.
I think, I'm sorry for interruption. I think we have some small problem with your microphone.
So you cannot hear me?
I can, but it's not so loud.
Okay, it's okay right now?
Yeah, it's okay. Thank you.
So my talk is based on two papers that I did with Giovanni Opava and Gorgios Kerachian. One of them is about dynamics of barotropic fluid in especially curved FRW spacetime, and the another one is about dynamics of non-minimally coupled scalar field in especially curved spacetime. But first of all, I would like to tell you about why we are interested in dynamical system in cosmology. The main reason is that because we want to consider early time as a source in the dynamical system and the late time as the sink in the dynamical system that we define. But the point is that our physical variables like energy density, scalar field, or let's say scale factor, they might be diverge or become zero at these two limits. So what should we do? We have to introduce normalization variables to derive the new variables in which we avoid these two, and we avoid singularity or divergence or the zero at these two limits. So first, I want to start with the barotropic fluids. We know that we can derive Friedmann equation, Richardo equation, and also we have the continuity equations for barotropic fluid. What do we assume here? We assume that energy density is positive, and then pressure is a general function or unspecified function of energy density. So it's generic function P is unspecified equation of state. And then what we are going to do, what we did in this work, we analyze the evolution of this system. So the first step to analyze the dynamical and to use the Friedmann equation, Richardo equation, as a dynamical system, we have to introduce the normalization factor. But what we did in this work, normally Hubble parameter is used as a normalization factor because in most work they study the flat cases. Here, since we are studying the spatially curved FRW spacetime, we define the new normalization factor in this form. And since K here is the absolute value, this normalization factor is valid for positive and negative curvature. Therefore, from this normalization factor, we can define our dimensionless variables or dynamical variables, which are omega epsilon, omega h, omega p, and omega dp, and also gamma. And the gamma is the function, and I will talk more about this function, but in general, this gamma function encodes the equation of the state, EOS. So the next step is to define the evolution parameter. So since our normalization parameter is d, the evolution parameter becomes like this. And the next step before deriving the autonomous system, we wrote the Friedmann equation in terms of our dimensionless variables. So for positive curvature equation of Friedmann equation becomes like this, and for non-positive curvature we have Friedmann equation as it is. And the point that why it's important, because most of the time we can eliminate one of the or ignore one of the dimensionless variables, and we can write it in terms of the other dimensionless variables from Friedmann equations. Then we can reduce the dimensionality of our variable space. So here we can ignore the omega epsilon, and the autonomous system can be written, it's only omega h prime, omega p prime, and omega dp prime. So these are the ordinary differential equations, and we know from the dynamical analysis that's what should we do with this kind of systems is to derive to find the critical points, and then to investigate for their stability, and then we should interpret them the physical interpretation of those critical points. And for this general system, as I told you, it's for unspecified equation of a state. We found 2 de Sitter critical lines, and also one static universe critical line, which are located at these points. And their stability of these points, I call the one of these points A plus for omega h equal to 1, and the another one A minus for omega h equal to minus 1. And these are the eigenvalues of these 2 points, and also this is for the static universe. But we don't know what is the value of omega dp, and we cannot then analyze the stability of these points. So, but we know that if 1 plus omega dp is positive, this point is source, and this point becomes sink, and this is a saddle point always, because different sign between these 2 eigenvalues. So these, let's say, 3 critical lines are the general critical lines of any barotropic fluids, but we can investigate more by keeping it almost general in the general case. We, as I told you, we have this gamma function, which I introduced it here. And you can see gamma is only a function of energy density epsilon, because P is a function of epsilon and this is epsilon. And if I want to write it in terms of the other dimensionless variables, we have we can use only omega dp and omega p over omega epsilon to eliminate this geometrical, to eliminate ds squared, because it's not related to energy density. So in general, if we want to write gamma as a function of other dimensionless variables, it can be a function of omega p, omega epsilon, and omega dp. But there are some cases that omega p over omega epsilon is related to omega dp. In some cases, and we studied these cases. That's if we write gamma as a function of omega dp, and also we assume that this gamma function has only one root, and that root is omega dp prime field. And so when gamma from this root, we can see that this equation becomes 0, and then we have only omega h prime and omega omega p prime as our dynamical variables. So we are in the invariant subset omega h omega p plane, and this omega dp creates the invariant subset. So in these invariant subsets, by keeping by assuming only these assumptions that gamma is a function of omega dp, we found more critical points. So 2 critical points we found, which is located at these 2 points, c plus c minus, with these eigenvalues, and 1 and 2 Milne critical points located at these points with these eigenvalues. So as I told you before, what should we do? We should investigate for the stability of these points. But as we see here, we have 1 plus 3 omega dp. Also here, for a plus a minus, we have 1 plus omega dp. So we can split our analysis into 3 different ranges, and then we can plot the invariant subsets for this case. If the first case is when omega dp greater than this one, minus 1/3, sorry, and the middle one is when omega dp between -1 and -1/3, and the last one is this invariant subset. So we see that, for example, in these invariant subsets, the whole invariant subset is divided into 3 regions, and these orange lines are separatrices of the system, and green area is the accelerated expansion of the universe. So, for example, in this region, it starts from expanding C plus to contracting C plus, which is like a recollapsing model. And here it starts from C plus and going towards the A plus. So it's like starting from expanding C plus to expanding de Sitter, and here from anti-de Sitter to C minus. But the physical interpretation of these C plus C minus are related to the value of omega dp, which for this case is the C fluid. And we can interpret the same in this way for the other invariant sets. This is for the case that's for the positive spatial curvature. And for negative curvature, we found this invariant subset. Here, the blue part is the part that's which is it's not physical. Why? Because if I go back to the Friedmann equation, we see that omega epsilon should be positive because we assume that energy density is positive. So this part should be positive. So omega h squared is, should be greater than 1/2. Therefore, this part is less than 1/2, so we ignore this part. The only physical subregion here is, let's say here, starting from C plus, go to the de Sitter, expanding de Sitter, and here from contracting de Sitter to the C minus, and here, for example, starts from D plus, which is Milne, and goes toward the expanding de Sitter. And here starts from the Milne universe, and it goes to the C plus. So what I have told you until this point, it was related to general equation of a state, but and we introduced this setup that's related to the unspecified equation of a state, but we found some critical points of all these equations. I mean, for barotropic fluid, which equation of a state is not specified. And we can use this general setup to, for example, I mean, here is an example to see how this general setup works. If we start from gamma function, which is linear to omega dp, and we assume that here we want to impose some assumptions, and from these assumptions we will see that how the invariant subset will be. So we assume that we impose the causality condition when omega dp is less than 1, and that means that beta is equal to minus alpha. And then we assume that when energy density tends to 0, pressure does not diverge, and also we assume that it can be we can get negative pressure. And also when we have large energy density, the pressure of the fluid we consider that to be positive. I mean, we ignore the early inflation. So by using this assumption from gamma function, we can derive at this equation of the state, which is the combination of stiff fluid and some exotic fluid. And for this equation of the state, the invariance of, our dynamical system reduced to two dimensional space, which one is omega dp and the another one is omega h. And we see that for this equation of a state, this setup starts from stiff fluid. This is the invariant subset divided into four subregions. The upper one starts from stiff fluid and goes to the expanding stiff fluid to contracting stiff fluid, which is recollapsing model. And the right subregions describe the universe, which starts from stiff fluid and goes to the accelerated expansion phase, and then to the de Sitter point. The left one starts from contracting de Sitter and goes to the contracting stiff fluid, and the lower subregion describes the bouncing model. It starts from the contracting de Sitter, goes to the expanding de Sitter. And this is for the positive curvature. For negative, for non-positive curvature, we have this invariant set, which starts from stiff fluid and goes to the expanding de Sitter. And here we have contracting de Sitter to the contracting stiff fluid, and this middle part is the part that I told you that we have to ignore it due to the Friedmann equation constraint. So this first part is related to the barotropic fluids, which I showed you that in general, for any equation of a state, what critical points we can get. And then I showed you that the example that we can, how we can use this general setup. The next
5 minutes.
Sorry,
5 minutes.
Okay. The next part of my talk is related to the non-minimally coupling scalar field, which we are familiar that we can start from the action of non-minimally coupling with this Lagrangian, and we can derive the Friedmann equation, Ricciardo equation, and also we have the Kellen-Gordon equation. Same as the previous case, we define the normalization factor, which is D, which is valid for both positive and negative curvatures, and then we define dimensionless variables which are well defined. I mean, well defined because each dimensionless variable is related to only one physical variable. And then, same as the previous case, we can write an equation in terms of the dimensionless variables, and they will work as a constraint for us. Autonomous system, and then we get from autonomous system one can derive the critical points of this system. So we have two de Sitter critical points for flat curvature, two de Sitter critical lines. I mean, and these are the location of these points and lines. And again, these are for flat curvature. We found two radiation-like critical points and also two Milne-like critical points. So this is again the general setup. They are not related to the scalar field potential. In general, one can get all these critical points for a dynamical system. And as an example, we can write, I forgot to tell you that here, this gamma is like is a tracking parameter, and in this one encodes again the potential of our system. So if we put gamma equal to 1, we get the exponential potential, and we have these invariant subsets for this case. For example, when omega dv is equal to 1, omega dv 0, and omega dv minus 1, we plotted this invariant subset. When s plus s minus, these 2 points, blue points, are singular points in our system, and these singular points are not related to the dimensionless variable that we define. They are related to the when we want to decouple Ricciardo equation and Klein-Gordon equation. This anomaly appears, and it's not related to the dimensionless variable that we derive. So we can see that, and we call them Big Bang because if we go back, when the time parameter tau, I defined it before, if it goes to -infinity, it goes to these 2 points, which are sources of our points, so we call them Big Bang, and then it goes to the accelerated expansion phase, the green area, and then goes to the sink, which is this Sitter point. And same for the other cases. This is for an expanding universe, and for contracting universe and omega h -1, we have the same figure, but they are inverse here. The Sitter points are our source, and s minus are sink, and we call them, and they are a big crunch in our system. So, and in the second part, same as the first part of my talk, what we did, we start to investigate, we start to analyze the non-minimally coupled scalar field with the generic potential. We derive the critical points of this system, and then I presented one example to see how this general setup works. So thank you very much.
Okay, thank you very much for a very nice talk. Thank you. So let's thank our speaker. Okay, thank you. Are there any questions? We have some time for 1 or 2. Okay, let me check. Anybody?